Hello, this is Miss Jody coming to you with our first video for chemistry. As I emailed your parents due to our separation for a while, I'm going to be making videos of the lessons so that you can work on them at home. It's my idea that we try to work on some of our notes for the journals to get them ready. And that way, when we're able to come back together, we'll have all of that accomplished, and we can spend some time doing some of the experiments and activities such that we like to do. Just happen to have these little cute photos here. Don't know why, but so we will be doing some of our activities and getting our pictures and our crafts and stuff for the journals when we return. Now, to keep the journals going, I am going to be creating the note pages and then you can take the notes at home. I do prefer for you to take them on a half sheet of paper. I'll give you an example. Like that. Like this. And do not forget that I will be putting a label at the top of your book. I'll be gluing these right into the journal. So don't forget that there is going to be the label right there, so to keep it consistent. So actually you should be able to write on the whole sheet of paper, and because of that, the whole half sheet. And all I did was just take a regular piece of computer paper and just fold it and cut it in half. So when you're taking your notes, just keep in mind that they will be glued into the journal along the way when we get back together. And I'll be keeping your journals all in order and the spaces provided for the experiments too, so we don't forget to do those when we return. Okay, so obviously we'll be using my notes that I've written in my journal, which usually have a lot of extra little doodads. And so you can slim it down a little bit as you're working so that you can pick out the main points, but don't slim it down too much. We still want to have some good notes that are good, because with the journals, what we do is we use this for our review, and it helps us whenever we have to go back and remember the concepts, and especially for studying for the end of the year exam. All right, so we just finished chapter, what was it, 12? And when we were together last, which was on heat, temperature, energy, the kilometer, whatever, calorimetry equations. And so now we're moving on to thermodynamics. Now we've already talked a little bit about thermodynamics, so some of this will be a review. And because the chapters are so long and there's so many topics, I'm going to make a few videos per chapter. That way you can do one topic, work on it, and then the next day maybe do another video and work on it. So I'm going to try to keep the topics together that go along with each other, and then take a break and then do the next set. Okay, so with thermodynamics, obviously we studied this before. It's the branch of science that deals with the relationships between heat and the other forms of energy, such as mechanical energy, electrical, chemical. So we're going to see the relations between heat and these other forms of energy, and specifically in chemistry, the chemical side of energy, the kinetic and also the potential side. So we've already talked about the endothermic and the exothermic in prior chapters, specifically Module 10. They note out that we talked about this in a sense of the physical change side of things, which is the dissolving whirl. So the solutes dissolving into the solutions, or into the solvents, creating the solution. And so in an endothermic situation, it's when solutes dissolve endothermically, they absorb energy and of course cool down, which we know. Exothermic is when solutes dissolve exothermically and they release energy and actually heat up to the touch. So we've done some experiments. In fact, that one that I just showed you a picture of don't know why I have so many pictures of Bo. These are the extra ones, and I've already put these pictures in your journal, Bo. I must have printed them twice. But remember, we were doing this particular experiment with the hot hands pack. So we had the exothermic side of things, but we've done many. And in fact, last time we met, the experiment that we were doing, creating the gases and isolating the hydrogen, that was pretty little hot mess there. So hopefully I can send onto the new Facebook page that I have that these videos will be on, the videos of that, so I can send them to you, because that's hilarious. But anyways, we'll do a better job when we get back together on creating these wonderful gases and not melting the actual apparatuses that we were trying to create them in. Okay, so maybe a little bit too much aluminum foil, a little bit too much of the caustic soda, something gone wrong there. Anyway, so we've done some endo and exothermic reactions for sure. Now this chapter specifically, instead of the physical change side of things, is going to move into the endo and exothermic world of chemical changes. And the chemical reaction that is endothermic, which absorbs energy, can be thought of in this chemical sense, especially with formula writing, as the reactant. So meaning, if a chemical reaction is endothermic, where did the energy go? Well, it's not in the end product. It's not on the product side, because it's the products you have produced are cold to the touch, and so that's an indicator. So where we put the energy that has changed in this situation, we put it on the reactant side. If a chemical reaction ends up being exothermic, the chemical reaction releases energy. The energy can be thought of as a product. So when you have a reaction take place and then it's really hot to the touch, it makes perfect sense that you think in your mind, okay, energy is being released because this is very, very hot. And so that one's easier to understand, that in an exothermic reaction, the energy will be thought of as the product. Now, these two terms are to get us to start thinking about this situation of absorbing and releasing energy more in a formula writing and understanding situation, so that we can keep track of these energies. Now, we know with the first law of thermodynamics tells us that the energy cannot be created or destroyed. We already know that. So energy is never really produced, nor is it really consumed. However, it just changes forms. But in the chemistry world, we think of it this way, as to track the movement, the whereabouts of what's happening between the chemical reactions. So it's necessary for us to think of it as the reactant product world. Okay? And so continuing with that thought, now it's taken me this whole page and one other page, but if it only takes you one page, you can just keep writing on the same page. But don't forget to not write on the back of the half sheets, because if you write on the back of the half sheets, I can't glue it in there. Okay, so if you have to go on to another page, just get another half sheet. All right, so continuing on. So if chemical reactions do not produce or consume energy, where does the energy come from? And that's what we're basically trying to keep track of when we start looking at the thermodynamics of chemical reactions. And so we know already the world of potential energy versus kinetic energy. Potential, stored up. We have stored up energy ready to be released. Kinetic is energy that has been released in motion. So where is this stuff going to be stored up? Well, in the chemical bonds of the substances that you are reacting to create your new products. And then the heat associated with absorbing or releasing during a chemical reaction is thought of as the kinetic side of it. So whether the stored up version of it is being absorbed back in, that's still movement, or if it's being released. So whether it's on the reactant side or the product side, it's still moving. And so that's the kinetic side of this chemical reacting thermodynamics. So endothermic, kinetic energy in the surroundings is absorbed and converted into the potential energy. So this is, in the endothermic side of things, is when you put two reactants together and then they create an endothermic reaction. The idea and the way to think of it is that the energy that it takes to break the bonds, to rearrange them to create the products, some of that gets absorbed back in on the reactant side. It's not all used up. Now, on the exothermic side, This is the potential energy that is stored and converted into kinetic energy. And so when we have an exothermic side of the reacting, we know that there was the potential energy in the bonds of the original reactants, and it had to be broken apart, and then breaking apart as it formed into the new products. We now have the products forming, and there is still going to be an energy release. Whether it's a lot of energy or a little bit of energy, it'll end up being all about the balance between how much is released on which side. And that will help us keep track of it, because in all reality, there's always a release of energy. It's just, where is it at? Which way is it going? So for instance, and in a simple version, we've got a simple equation here. Hydrochloric acid reacted with sodium hydroxide as the base, so an acid-base reaction, which we know then creates water and salt. So we got our H2O and we got our NaCl. And in this reaction, it's an exothermic reaction, and we know because the energy is on this side, so the side of the products and it being released. And then if we have another reaction here, you see the reactants, this, whatever in the world that is, and then this reacting to create this product, and 8 H2O molecules. Couldn't fit that in there, and I couldn't then fit the energy side on here. In this reaction, the energy ends up, this becomes an endothermic reaction, and it's cold to the touch, and the energy has been released and absorbed here. And so the energy is on this side. So this would give us an indication that this is an endothermic reaction. So if you have just something simple and you see energy on that side, exothermic. If you see energy on this side or the reactant side, then it's endothermic. Now, of course, it gets way more complicated than this, but this is the beginning idea of trying to keep track of the energy. Now, the next topic, which is that very thing, keeping track of the energy and figuring out the actual change that has taken place. That's where the calculations begin. All right, so this is the world of enthalpy. Enthalpy is the energy stored in a substance, and the symbol that they use is H. And again, trying to keep track of all these symbols, and even in the book it says they don't know why they use that symbol, and hopefully just the more we continue with calculations and equations, we can keep track of all these little doodads, right? So H is going to be the symbol for enthalpy, and what that's going to represent here is the energy that's stored in the substance, and we want to figure out when we create the reactions how much changes in where it goes. So this is why the delta is going to be added to the enthalpy symbol. So this will create the energy change that accompanies a chemical reaction. It does say in the book, and I've seen this in other books, that it's often referred to just as the enthalpy of the reaction, and that's not really accurate, because enthalpy is the energy stored in the substance. So if I have a substance like hydrochloric acid, I can say how much is stored in there, how much is actually stored in there. I'm not talking about it changing. So you really should have the word change in there when you put this together. If you're just talking about the enthalpy in the substance, then of course that. But because they take that word and they add it to reaction, they're assuming you know that it means change in enthalpy. Okay, so when we're looking at these types of reactions, we're going to keep track of what's happening, where it's going, and how much. And when we keep track of it, we're going to be using units, just like all of our calculations. And the units are familiar to us because we just worked in this chapter on energy and temperature and heat and all that. And so we have the 2 units for the energy release, which is the calorie of the joule, and we have the calculation, or the units there. 1 calorie is equal to 4.184 joules. And however, in these types of reactions, usually they say there's a lot of energy that's being released, so many times you're going to see kilocalories or kilojoules. So with this kilocalories, kilojoules, we can't stop there, because that's just about the amount of energy. And it says in the book, like, say if you're going to do a reaction between this and this, if you have a small amount and then 2 small reactants, and you react them together, compared to two larger amounts of reactants, you could have a different amount of energy release. So it has to have a comparison to the amount of the reactants undergoing the change. So you got to have a second thing to your unit. So the amount of reactants undergoing the change, they focus on a mole by mole basis. So basically what this means is we take the kilocalorie per mole or the kilojoule per mole. And that's because we're getting a base of 1 mole to watch the energy of 1 mole of that substance, whether it's being absorbed or whether it's being released. We're going to figure out how much energy of just 1 mole is either absorbed or released. And so 1 mole equals the energy absorbed or released of that substance. Now, when we keep track of this, if we end up having a ending calculation that's positive, then we will have, once we do all the calculations, learn how to do that, we will have an endothermic relationship if the change is positive, or a reaction. And then if the change is negative, then we will have an exothermic. Now, the way I remember it, and helps me make more sense, endo, I'm going to bring it in, I'm going to have more. Exo, I'm going to have released it, let it go, lost it, subtracted. Okay? Now, what I'm going to do for the calculations, and I urge you to do this so that you're practicing them just like we'd be doing on the board, is I'm going to write out the equation, or I mean the little practice problem, and then I'm not going to write the answer there. And then later on a different video, I'll fill out the answer side. And of course, because I take a lot of these problems from the book, you should not be using your book at the time when you practice your work side of it, okay? So I'm going to just highlight these so I can remember to go back and do them. And then that way you practice it yourself, and then we can see what the answer is in the end. So you can just pause the video, practice it, and then start the video back up for the next one. And then, like I said at the end, for both of the problems, I will, and maybe more, we'll do a different video for that. Okay, so this question, when CH4 undergoes complete combustion, which we know what complete combustion means, the change in enthalpy of the reaction is negative 803.1 kilojoules. It tells you to write a balanced equation representing this process and include energy in your equation. So what they're wanting you to do is to basically set up an equation like this, where you figure out what's happening, which we know with CH4 and undergoing complete combustion, what else would be in that equation, and then figuring out the energy amount, which they've already given you, and putting it on the right side, whether it's in the product or the reactant side. Okay, so go ahead and pause the video and then do that particular problem. Okay, the next thing of this topic, and it goes along with this, is bond energies. Okay, so if you did that problem, then you'll be on your way to starting to figure out where the energy is going in the reactions. And what we have to focus on is we need to know, we've already talked about the energy, where is it? Where is it coming from? Well, it's stored in the bonds of the original substances that you are reacting. And so when chemical reactions occur, chemical bonds are broke. So we know that because then they break apart and they rearrange. So rearrangement takes place to create the necessary configuration to make the products, in which the new chemical bonds are then made. So you've got to break bonds, then rearrange, and then form bonds. And during that time, there's a lot of energy things going on here. So say, for instance, this is the example they give us, CH4 plus 2 moles of O2 will react to create carbon dioxide and 2 moles of water. And so if you draw this out, you've got CH4, and there's your Lewis dot structure, plus then you've got your carbon dioxides in a double bond, and then you have, 2 oxygens, not carbon dioxide, O2. You have O2 and O2, two sets of it. And then you have your carbon dioxide, and that's two double bonds with the C there of the O. And then you got your H2O. Okay, so in drawing out the Lewis dot structure, we begin to be able to see the energy that is in these particular bonds. Okay, so we have to realize in order for this to break apart and form this on the product side, there's going to need to be energy to break the bonds, and there's going to be need energy to make the new bonds. And so when we think of the energy to break the bonds, energy being absorbed by the reactants during the bond breaking. So what happens if you have something like really strong bonds, there's going to need to be a lot of energy to break that. And so there's going to be that absorption of the energy to actually break it. And then energy to make the new bonds. Energy, and this is something that's hard to get your mind around, but energy to make the new bonds, energy is being released each time the products form. Even if we have an endothermic side of a reaction, there's still energy on that other side. It's just because there still has to be a forming going on of those bonds. So we have to keep that in mind. So really it's all about the balance. The balance side of things, of how much is going where, is what creates the endo and the exo side of things. So an example they give us, okay, so they say if the reactants are really strong, so on this side of the equation, it takes a lot of energy to break the bonds. So the reactants tend to absorb a lot of energy because so much energy is needed to break them. So if they were actually broke, then they would have had to have a lot of energy to get that to happen. And so on the product side, with let's say if the products have weak bonds, so on the product side we have bonds that are weaker, then when they are formed, the products release only a small amount of energy. So if you're a weaker bond, you're only going to release a smaller amount of energy. So when we look at this, there was more energy on this side, so much more energy that it took to break the bonds than to release it. So therefore, it would have been an endothermic reaction because you could have never gotten these to break up if you didn't have a whole bunch of energy going on this side. And then vice versa, then when you still had some energy forming the products on the other side, it just was a little bit weaker. So that's where that back and forth balance will be. Now, with bond energies, we have the world of the bond energy itself. What does that mean? It's the measurement of the strength of the chemical bond. And we've seen this before with doing Lewis dot structures. You got single bonds, you got triple bonds, you got double bonds, whatever. Well, what happens is in order to break it or to make it, you need a certain amount of energy. So let's say, for instance, if you have carbon bonded with a single bond with hydrogen, you're going to need 411 kilojoules per mole to break that bond. And so you need a lot of energy to break it. But not only that, you need 411 kilojoules per mole to make it. So if you want that bond to happen, you need that much energy to create or to force that bond to be formed and force them together. And so these are just some examples. They give some examples in the book, but this is of a few different molecules. So I wrote a few down so we could see. You can see here with N2, which is nitrogen, what we call molecular nitrogen. And because we've got those three bonds there, I mean, that's a strong bond. You're going to need 942 kilojoules per mole to break it or to make it. And this really makes sense, especially when you think back into your times with biology and ecology and understanding like the nitrogen cycle and how much we need nitrogen, but yet it's in its molecular form and in our air mixture. And so we can't just go around splitting it, and using and getting it into the forms we need. But lightning strikes and splits the nitrogen, and then it can create bonding with other things to create the nitrogen forms that we actually need. And so when I think of nitrogen N2 anyway, I always think of like lightning, which makes a lot of sense. You need a lot of energy to bust it apart, and then of course to put it back together. And we have those lots of microorganisms and such that work on breaking it and putting it back together for us so that we can have it for our usable source of nitrogen. But so say carbon and oxygen, a double bond, you need 799 kilojoules per mole. Bromine, a single bonded set of 2 BRs, you only need 190 kilojoules per mole. So the thing is, no chemistry class requires you, well, I shouldn't say no chemistry class, there's probably one, but most chemistry classes would not require you to memorize anything like this. There's charts in your book, or you can look those things up online. And so basically all you'd have to do is you'd have to figure out what bonds are really there between what atoms in your substances as you're putting them through a chemical reaction, and then figure out each one of those particular bond energies and then use that to calculate your change of enthalpy. Okay, so there is a standard here with the mole side too. We have to remember how much energy is required to break 1 mole of those bonds. So this is why we also have a unit measurement of that along with the energy of the mass. Okay, so then we have a little mathematical way of looking at it. So your change of enthalpy of the reaction mathematically will be as such: energy required to break the bonds, and then minus the energy released when the bonds form. So because we need energy to break it, and then there's energy in the making of it and energy released when it's made, then we have to keep track of all that. And this is what you would do mathematically. So any of the equations that we work on for the bond energies, they're always going to require you to create a Lewis dot structure. If you forget how to do the Lewis dot structures, can't remember, it's chapter 8, but I think all of you guys are real good at the Lewis dot structure, so it shouldn't be that big of a deal. But you will have to draw out, which I didn't give myself a lot of room here, did I, for drawing out those Lewis dot structures. Hopefully I can make it smaller, do it on another piece of paper. But so when we do a problem, again, like I said before, just pause the video, try it out, and then I'll make the answer video on a different one. Okay, and of course, these are in your book, so don't look in your book, no cheating. Okay, so to make ammonia, nitrogen and hydrogen are reacted at high temperatures to this equation. So you take the nitrogen, you take the hydrogen at high temperatures, which is going to give us an information here that we're going to have some energy involved. Then what is the change of enthalpy? There I go again, to relook at it. Enthalpy, there we go. My pronunciations. All right, so what is the change of enthalpy for this reaction? And is it endo or is it exo? So you would draw out what you need to draw out and figure it out. Now, of course, you will use the bonds, the amount of energy that you would use a chart in the book. Once you draw this out, well, we already know N2, it would be 942 kilojoules. So you just have to figure out what happens in a bond of H2. And I think the chart is on, without looking at any of the answers to the questions, the chart is, excuse me, on page 456. And a H2 is 432 kilojoules per mole. And then, let's see. Okay, so you would just use the chart to figure out the amounts and use this information on energy required to break the bonds minus the energy released when the bonds form to give you the answer, okay? And whether it's endo and it's exo. And then I have one more practice one for this, and this is the end of this particular part of the chapter. Like I said, I'll do multiple ones so it's not so ongoing without a break. And that way you can practice a little bit. And this one is, and if you need an extra page like I did, just keep making pages and we'll glue them in accordingly. Okay, so this one says the complete combustion of methyl alcohol, which is CH3OH, is used to power some experimental automobiles. What is the enthalpy of that reaction? So obviously you have to create the equation too. complete combustion, which we know what complete combustion, the products and what it needs to react with. So you create your reaction and then you do your math on figuring out, draw out your Lewis dot structures, do the math to figure out what you end up having. And as a reminder, if your numbers end up being negative, you have what? If you look back, your negative side of things, then you have an exothermic because it was released, and a positive, you have an endothermic situation. Okay, alrighty. So you work on that, and then I will see you in the next video.